Deep in the constellation Leo, 120 light-years from Earth, a telescope has captured something that will change everything we thought we knew about life in the universe. The James Webb Space Telescope has detected a world where the temperature hovers at exactly 120 degrees F, wrapped in an atmosphere that pulses with the chemical signature of living creatures. Scientists are 99.7% certain they've found it. A planet teeming with life, more habitable than Earth itself. Like and subscribe as we journey to witness humanity's greatest discovery. Prepare yourselves. We begin. The data. The data arrived on a Tuesday morning in December, buried in terabytes of infrared light captured by humanity's most powerful eye in space. Niku Magison stared at his computer screen at Cambridge University, watching wavelengths of light that had traveled 120 light-years to reach Earth. What he saw made his hands tremble. There, in the spectrum of light filtered through an alien atmosphere, was a signature that shouldn't exist: dimethyl sulfide, a molecule that on Earth is produced only by living organisms. Not just a trace, but a signal so strong that the odds of it being a mistake were less than 3 in 1,000. The James Webb Space Telescope had found what every scientist had dreamed of: undeniable evidence of life beyond our solar system. The planet. The planet designated K218b orbits a red dwarf star in the habitable zone where liquid water can exist. But this world is unlike anything in our solar system. 6 times more massive than Earth, wrapped in a hydrogen-rich atmosphere that creates a greenhouse effect so perfect that vast oceans remain liquid beneath alien skis. The temperature readings were stunning: 120 degrees F, warm enough for life to flourish, yet cool enough to prevent the complete evaporation of water. Madhusudan's team had been studying this world for months, using JWST's incredible sensitivity to peer through the planet's atmosphere as it passed in front of its star. Each transit revealed new secrets. First came the detection of water vapor, then methane, then carbon dioxide. But dimethyl sulfide was the game changer, a molecule so intimately connected to biological processes that finding it in an alien atmosphere was like discovering a neon sign advertising life. The implications hit him like a physical blow. If confirmed, this discovery would end humanity's cosmic loneliness forever. We would no longer be alone in the universe. The evidence. The probability calculations were staggering: 99.7% confidence that the signal was real, not noise or contamination. In the world of astronomy, where certainty is rare and discoveries are often overturned, this level of confidence was unprecedented. But K218b wasn't just any world. Its unique characteristics made it potentially more habitable than Earth itself. The hydrogen atmosphere acts like a massive blanket, trapping heat and creating stable conditions across the planet's surface. Unlike Earth's thin nitrogen atmosphere, this thick envelope of hydrogen could support liquid water across a much broader range of temperatures and pressures. The star. The star K218 is a red dwarf, smaller and cooler than our Sun, but also far more stable. While our Sun will eventually expand into a red giant and destroy all life on Earth, red dwarfs burn for trillions of years, providing stable energy for eons. Any life that evolved on K218b would have virtually unlimited time to develop complexity beyond our imagination. As Madhusudan prepared to share his findings with the world, he realized that December morning would be remembered as the moment everything changed, the moment humanity discovered it was not alone. But this was just the beginning of a story that would reshape our understanding of life, the universe, and our place within it. Rethinking habitability. Scientists once believed we needed to find Earth's twin, a rocky planet orbiting a sun-like star at just the right distance for liquid water. K218b shattered that assumption completely. This world proved that life could emerge in conditions so alien that we never thought to look for them. The planet belongs to a class called super-Earths, worlds larger than our own but smaller than Neptune. Until recently, astronomers dismissed these planets as inhospitable gas balls, too massive to support life as we know it. K218b forced scientists to completely reimagine what a habitable world could look like. Its mass creates surface gravity nearly 3 times stronger than Earth's. A person weighing 150 lb on Earth would weigh over 400 lb on K218b, yet this crushing weight might actually benefit life. The intense gravity holds the atmosphere in place, preventing it from bleeding away into space, like Mars lost its atmosphere billions of years ago. The atmosphere. The atmosphere itself defies everything we thought we knew about habitable worlds. Instead of the oxygen and nitrogen we breathe, K2-18b's atmosphere is dominated by hydrogen and helium. On Earth, hydrogen is a trace gas, making up less than 1 part per million of our atmosphere. On K2-18b, hydrogen comprises the vast majority of the atmospheric envelope, creating a completely alien environment. This hydrogen atmosphere creates what scientists call a runaway greenhouse effect, but in reverse. Instead of cooking the planet like Venus, the hydrogen acts as a perfect insulator, maintaining stable temperatures across the planet's surface. The thick atmosphere redistributes heat so efficiently that even the night side of the planet, which never sees sunlight, remains warm enough for liquid water. The chemical signatures detected by JWST paint a picture of a world where life has not only emerged but thrived, alongside the life-indicating dimethyl sulfide. The atmosphere contains methane, carbon dioxide, and water vapor, a cocktail of molecules that suggests active biological processes. On Earth, these same gases are produced by everything from bacteria to complex organisms, creating a planetary metabolism that can be detected from space. But perhaps most shocking is what's missing from K2-18b's atmosphere: the lack of ammonia, a molecule that would dominate if the planet were a lifeless gas giant, provides strong evidence that biological processes are actively removing it from the atmosphere. Life is not just present on this world, it's actively shaping its atmospheric chemistry. A universe full of life. The discovery of K2-18b reveals that the universe might be teeming with life in places we never thought to look. If life can emerge and thrive in the hydrogen-rich atmosphere of a super-Earth, then the number of potentially habitable worlds in our galaxy could be hundreds of times larger than previously estimated. Red dwarf stars like K2-18, which make up 3/4 of all stars in the galaxy, suddenly become prime targets in the search for extraterrestrial life. The implications are staggering. We may not be looking for Earth's twin after all. We may be looking for Earth's strange cousin, thriving in conditions so alien that we're only now beginning to understand them. The James Webb Space Telescope. The James Webb Space Telescope is not just humanity's most powerful space observatory. It's a time machine that peers deeper into the cosmos than any instrument ever built. Floating 1 million miles from Earth at a gravitational balance point called L2, Webb exists in perpetual darkness, its massive sunshield blocking heat and light from our star to keep its instruments colder than the surface of Pluto. The telescope's primary mirror stretches 21 ft across, nearly 3 times wider than Hubble's. But size alone doesn't explain Webb's revolutionary capabilities. The mirror is composed of 18 hexagonal segments, each coated with a microscopic layer of gold that reflects infrared light with unprecedented precision. When these segments work together, they create a mirror so perfectly aligned that it can detect the heat signature of a bumblebee on the moon. Coronagraph technology. Infrared light is invisible to human eyes, but it's the key to detecting life on distant worlds. When planets pass in front of their stars, a tiny fraction of starlight filters through their atmospheres before reaching Earth. Different molecules absorb specific wavelengths of infrared light, creating unique fingerprints that Webb can detect with extraordinary sensitivity. The challenge of finding these molecular signatures is almost incomprehensible. Imagine trying to detect the light from a firefly hovering next to a blazing searchlight from 1,000 miles away. The star K2-18 is billions of times brighter than the planet orbiting it. Yet, Webb can pick out the faint infrared glow of molecules in the planet's atmosphere with pinpoint accuracy. Webb's secret weapon is its coronagraph technology. Originally designed to block starlight and reveal objects hiding in the glare, advanced image processing techniques subtract the overwhelming brightness of the star, leaving behind the faint infrared signatures of atmospheric molecules. It's like using a sophisticated filter to remove the roar of a jet engine so you can hear a whisper underneath. The detection. The detection of dimethyl sulfide on K2-18b required Webb to operate at the very limits of its capabilities. The molecule produces an infrared signature, so faint that it took multiple observations over several months to confirm its presence. Each observation captured just a few photons of light that had traveled 120 light-years through the vacuum of space, carrying information about life on another world. But Webb's most remarkable achievement might be its ability to measure temperature with incredible precision. The telescope detected that K2-18b maintains a surface temperature of exactly 120 degrees F, warm enough to support liquid water, but cool enough to prevent complete evaporation. This temperature reading, accurate to within a few degrees across interstellar distances, represents one of the most precise measurements ever made of an exoplanet's environment. The data. The data processing required to extract these discoveries from raw infrared observations involves some of the most advanced computer algorithms ever developed. Artificial intelligence systems analyze millions of data points, searching for patterns so subtle that they would be invisible to human observers. The discovery of life on K218b represents not just a triumph of engineering, but a testament to humanity's ability to push the boundaries of what's possible. Webb has fundamentally changed our relationship with the cosmos. We're no longer just wondering if life exists elsewhere. We're actively watching it breathe. Temperature. 120 degrees F, the number seems almost too perfect to be real. It's the temperature of a hot summer day in Death Valley, the warmth of a relaxing hot tub, the heat of a fevered human body fighting infection. On K218b, it's the temperature that makes life possible across an entire world. Temperature is everything when it comes to life. Too cold and water freezes into ice that can't support the complex chemical reactions life requires. Too hot and water boils away into steam, leaving behind a lifeless desert. The range where liquid water can exist, what scientists call the habitable zone, is surprisingly narrow. Earth sits almost exactly in the middle of this zone around our sun, a cosmic accident that allowed life to flourish for billions of years. But K218b's perfect temperature isn't an accident. It's the result of a delicate balance between stellar energy and atmospheric chemistry that creates conditions more stable than anything found on Earth. The planet orbits its red dwarf star at a distance where it receives almost exactly the same amount of energy per square meter as Earth receives from our sun. This cosmic coincidence means that, despite being 120 light-years away, K218b exists in essentially the same thermal environment as our own world. The hydrogen atmosphere plays a crucial role in maintaining this perfect temperature. Unlike Earth's thin nitrogen atmosphere, which allows heat to escape rapidly into space, K218b's thick hydrogen envelope acts like a planetary blanket. The hydrogen molecules trap infrared radiation, creating a greenhouse effect that keeps the planet warm even on the night side, which never sees sunlight due to the planet's locked rotation. This stable temperature creates something unprecedented in our solar system, a world where liquid water can exist everywhere, from the perpetual day side to the eternal night side. On Earth, temperature variations between day and night, summer and winter, poles and equator create complex weather patterns and climate zones. On K218b, the thick atmosphere redistributes heat so efficiently that the entire planet maintains a consistent, life-friendly temperature. The implications for life. The implications for life are staggering. Earth's temperature variations create stress on living organisms, forcing them to adapt to seasonal changes, migrate to survive winter, or develop complex physiological mechanisms to regulate their internal temperature. On K218b, life would face no such challenges. The stable temperature would allow organisms to invest energy in growth, reproduction, and evolution rather than survival. But perhaps most remarkably, the 120 degrees temperature on K218b falls within the range where life as we know it can not only survive, but thrive. Laboratory experiments have shown that biological processes can operate efficiently at temperatures up to 250 degrees F at 120 degrees. Chemical reactions proceed rapidly enough to support complex metabolism, while remaining cool enough to prevent the breakdown of essential biological molecules. The discovery of K218b's perfect temperature represents more than just a scientific curiosity. It's proof that the universe can create conditions for life that are not just habitable, but potentially more hospitable than Earth itself. In a cosmos where most planets are either frozen wastelands or molten hellscapes, K218b stands as a beacon of hope, a world where life doesn't just survive, but flourishes in perfect comfort. Dimethyl sulfide. Dimethyl sulfide, the name might sound like a chemical tongue twister, but these three words represent the most important discovery in human history. When the James Webb Space Telescope detected this molecule in the atmosphere of K218b, it found something that has never been produced by any known non-biological process. It found the signature of life itself. On Earth, dimethyl sulfide is produced exclusively by living organisms. Phytoplankton in our oceans create this molecule as a byproduct of their metabolism, releasing it into the atmosphere where it influences cloud formation and weather patterns. Marine bacteria, certain types of algae, and even some plants produce dimethyl sulfide as part of their normal biological processes. No geological process, no chemical reaction, no non-living system has ever been observed creating this molecule. The detection of dimethyl sulfide on K218b is revolutionary because it represents what scientists call a biosignature, a molecule that can only be produced by life. Unlike oxygen, which can be created by non-biological processes, or methane, which can leak from geological formations, dimethyl sulfide has no known abiotic source. Its presence in K218b's atmosphere is as close to proof of life as we can get without actually seeing the organisms that produce it. The chemistry of life. The molecule's chemical structure tells a story of biological complexity. Dimethyl sulfide consists of sulfur atoms bonded to carbon-containing methyl groups, a combination that requires specific enzymes to create. These enzymes evolved on Earth over billions of years, developing as part of the sulfur cycle that helps regulate our planet's atmospheric chemistry. The fact that similar molecules exist on K218b suggests that life there has also evolved sophisticated biochemical pathways. But the most shocking aspect of the discovery is the abundance of dimethyl sulfide in K218b's atmosphere. The concentrations detected by Webb are orders of magnitude higher than what would be expected from a planet just beginning to develop life. This suggests that biological processes on K218b are not just present, they're thriving on a planetary scale. A planetary biosphere. The implications are staggering. If life on K218b is producing dimethyl sulfide at levels detectable from 120 light-years away, the biosphere must be enormous. We're not talking about microscopic organisms struggling to survive in isolated pockets. We're talking about a planetary ecosystem so vast and productive that it's actively changing the chemistry of an entire world's atmosphere. The discovery also raises profound questions about the nature of life itself. If organisms on K218b are producing dimethyl sulfide, they must have evolved similar biochemical pathways to life on Earth. This suggests that the basic chemistry of life, the use of carbon, hydrogen, oxygen, nitrogen, and sulfur to build complex molecules, might be universal. Life might not just be common in the universe, it might follow predictable patterns wherever it emerges. A turning point. The detection of dimethyl sulfide represents more than just a scientific breakthrough. It's the moment humanity discovered that we're not alone in the universe. Somewhere 120 light-years away, under alien skies. And in hydrogen-rich air, life is breathing, growing, and fundamentally changing the chemistry of an entire world. For the first time in human history, we have evidence that life exists beyond Earth. In the world of science, certainty is a rare and precious commodity. Scientists speak in probabilities, statistical confidence levels, and margins of error. They hedge their bets, qualify their statements, and acknowledge uncertainty. But when the James Webb Space Telescope data on K218b was analyzed, the numbers told a story so clear that even the most conservative scientists couldn't ignore it. There was a 99.7% chance that the dimethyl sulfide signal was real. To understand what this means, imagine flipping a coin 1,000 times. The probability of getting heads or tails on any single flip is 50%, but the probability of getting heads 997 times out of 1,000 flips is so small that it would never happen by chance in the entire history of the universe. That's the level of statistical confidence scientists have in the detection of life on K218b. Sigma detection. The confidence level comes from a sophisticated statistical analysis called sigma detection. In particle physics and astronomy, scientists use sigma levels to measure how likely it is that a signal represents a real discovery rather than random noise. A 3 sigma detection means there's a 99.7% chance the signal is real, only a 3 in 10,000 chance it's a false alarm. This is the same statistical threshold used to discover new subatomic particles, confirm the existence of gravitational waves, and validate the most important discoveries in modern science. But reaching this level of confidence for an exoplanet atmosphere required unprecedented precision. The dimethyl sulfide signal is extraordinarily faint, just a few parts per billion in the infrared spectrum. To detect it, Webb had to measure wavelengths of light to an accuracy of 1 part in 10 million, like measuring the width of a human hair to the precision of a single atom. The analysis involved multiple independent observations over several months, each confirming the presence of the dimethyl sulfide signature. Different instruments on Webb detected the same molecular fingerprint at different wavelengths, providing redundant confirmation of the discovery. Computer algorithms analyzed millions of data points, searching for systematic errors or contamination that could explain the signal. None were found. Ruling out alternatives. The statistical analysis also considered alternative explanations for the signal. Could it be caused by unknown atmospheric chemistry? Could it be contamination from Earth? Could it be an artifact of the telescope's instruments? Each possibility was tested and ruled out with mathematical precision. The only explanation that fits the data is biological production of dimethyl sulfide by living organisms on K2-18b. This level of certainty is almost unprecedented in exoplanet science. Most discoveries of atmospheric molecules on distant worlds are reported with much lower confidence levels, often barely reaching the threshold for publication in scientific journals. The 99.7% confidence in the K2-18b biosignature represents a quantum leap in our ability to detect life beyond Earth. The implications of this statistical certainty extend far beyond astronomy. When scientists say they're 99.7% certain that life exists on K2-18b, they're making a statement as reliable as any fact in science. It's as certain as the existence of DNA, as solid as the theory of relativity, as established as the age of the universe. We are no longer wondering if life exists elsewhere. We know it does. The hydrogen ocean. Beneath the alien skis of K2-18b lies an ocean unlike anything in our solar system. It's not made of water alone, but of water mixed with hydrogen under pressures that would crush any Earth-based life form. Yet, this hydrogen ocean might be the most life-friendly environment in the known universe. The ocean exists because of K2-18b's unique atmospheric chemistry. The planet's hydrogen atmosphere doesn't just float above the surface. It dissolves into the liquid water, creating a solution that remains stable across a much wider range of temperatures and pressures than pure water. This hydrogen-water mixture can exist as a liquid from near freezing to over 300 degrees F, giving life an enormous range of conditions in which to thrive. On Earth, the deepest parts of our oceans are under crushing pressure, nearly 1,000 times greater than at the surface. Most life forms cannot survive at these depths, limited by the pressure that would collapse their cellular structures. But on K2-18b, the hydrogen in the water acts like a natural pressure buffer, allowing the liquid to maintain properties similar to water at much lower pressures, even at great depths. Atmospheric stability. The hydrogen ocean also solves one of the biggest challenges for life on exoplanets: atmospheric loss. Earth's atmosphere is slowly bleeding away into space, and in a few billion years, our planet will become as airless as Mars. But K2-18b's hydrogen ocean acts like a massive atmospheric reservoir. As hydrogen is lost to space, more dissolves out of the ocean to replace it, potentially maintaining a stable atmosphere for trillions of years. This hydrogen ocean opens up possibilities for life that don't exist on Earth. Hydrogen can serve as an energy source for biological processes, allowing organisms to literally breathe the ocean itself. On Earth, some bacteria can metabolize hydrogen, but they're limited by its scarcity in our atmosphere. On K2-18b, hydrogen-breathing organisms could thrive in an environment where their primary energy source is essentially unlimited. But perhaps most remarkably, the hydrogen ocean could support life forms that are completely transparent to our conventional methods of detection. Traditional searches for life focus on oxygen-producing organisms like plants and algae. But on K2-18b, the primary life forms might be hydrogen-metabolizing organisms that produce entirely different chemical signatures. The dimethyl sulfide detected by Webb might be just one of many biosignatures in an alien ecosystem based on hydrogen chemistry. Depth and complexity. The ocean's depth remains a mystery. Computer models suggest it could be hundreds of miles deep, far deeper than any ocean on Earth. This vast volume of liquid water mixed with hydrogen could harbor ecosystems of unimaginable complexity and diversity. The stable temperature and pressure conditions could allow life to evolve in ways impossible on Earth, potentially reaching levels of complexity that we can barely imagine. The discovery of K2-18b's hydrogen ocean represents a fundamental shift in our understanding of habitable environments. We're no longer looking for worlds like Earth. We're looking for worlds that might be better than Earth. In the hydrogen oceans of super-Earths around red dwarf stars, life might not just survive, but flourish in ways that make Earth's biosphere seem limited by comparison. The universe's most life-friendly environments might be the ones most alien to our experience. Atmospheric chemistry. The atmospheric chemistry of K2-18b reads like science fiction, but it's real and it's spectacular. While Earth's atmosphere is a simple mixture of nitrogen and oxygen, K2-18b's atmosphere is a complex cocktail of molecules that create conditions both alien and surprisingly familiar. Methane swirls through hydrogen clouds. Carbon dioxide forms crystalline structures in the upper atmosphere, and under the right conditions, carbon atoms compress into diamond rain. Methane and carbon cycle. The methane in K2-18b's atmosphere tells a story of active biological processes. On Earth, methane is produced by everything from bacteria in swamps to cows digesting grass. It's one of the most common products of biological activity. Yet, it's also highly reactive, breaking down in the atmosphere within a few decades. The fact that Webb detected substantial amounts of methane on K2-18b means something is actively producing it in vast quantities. But the methane on K2-18b serves a purpose beyond just being a byproduct of life. In the hydrogen-rich atmosphere, methane acts as a crucial component in the carbon cycle, helping to regulate the planet's temperature and atmospheric chemistry. Organisms on K2-18b might actually breathe methane, using it as an energy source in ways that would be impossible on Earth. Diamond rain. The atmospheric pressure on K2-18b creates conditions that would seem magical to Earth-based observers. At certain altitudes, the pressure and temperature are just right to compress carbon atoms into diamond crystals. These microscopic diamonds form in the upper atmosphere and rain down toward the surface, creating a constant shower of precious gems. But to the life forms on K2-18b, these diamonds might be as common as raindrops are to us. Carbon dioxide and photosynthesis. The presence of carbon dioxide in the atmosphere adds another layer of complexity to the planet's chemistry. Unlike Earth, where carbon dioxide is a trace gas, K2-18b's atmosphere contains substantial amounts of CO2 that interact with the hydrogen and methane in complex ways. This three-way chemical dance creates conditions that could support entirely different forms of photosynthesis than anything found on Earth. Atmospheric dynamics. The atmospheric dynamics on K2-18b are driven by the planet's locked rotation, where one side always faces the star, while the other remains in perpetual darkness. This creates massive atmospheric currents that carry heat, moisture, and chemical compounds from the day side to the night side. The result is a planet-wide weather system that constantly mixes and redistributes the atmospheric chemistry, creating conditions that remain stable across the entire surface. The thick atmosphere also protects any surface life from harmful radiation. Red dwarf stars like K2-18 are known to produce powerful flares that could sterilize planet surfaces. But K2-18b's dense hydrogen atmosphere acts like a natural shield, absorbing and deflecting radiation that would be lethal to Earth-based life. This protection might be crucial for allowing complex life to evolve and thrive on the planet's surface. Biochemical possibilities. The chemical complexity of K2-18b's atmosphere suggests that life there might be far more sophisticated than anything on Earth. In an environment where diamonds rain from the sky and methane serves as breath, evolution might have taken paths that would seem impossible to us. The biosignatures detected by Webb might be just the beginning of a biochemical story that rewrites our understanding of what life can be. We're not just discovering life on another world, we're discovering life in another universe of possibilities. Red dwarf stars. K2-18 is not a star like our Sun. It's a red dwarf, smaller, cooler, and dimmer than the star that lights our world. But this seemingly modest star might be the most important type of star in the universe when it comes to supporting life. While our Sun will eventually expand into a red giant and destroy all life on Earth, K2-18 will burn steadily for trillions of years, providing stable energy for eons that dwarf the entire age of the universe. Red dwarf stars make up about 75% of all stars in the galaxy, making them the most common type of star in the cosmos. They're small, typically less than half the mass of our Sun, and they burn their nuclear fuel so slowly that they can maintain steady energy output for periods longer than the current age of the universe. While our Sun has a lifespan of about 10 billion years, red dwarfs can shine for up to 10 trillion years. This incredible longevity has profound implications for life. On Earth, complex life took nearly 4 billion years to evolve from simple bacteria to the diverse ecosystems we see today. If life on K2-18b has had even a fraction of the time available around its red dwarf star, it could have reached levels of complexity and sophistication that make Earth's biosphere seem primitive by comparison. A quiet star. The star K218 is relatively quiet compared to some red dwarfs, which are known for producing powerful stellar flares that could sterilize planet surfaces. These flares can increase a star's energy output by thousands of times for hours or days, bombarding nearby planets with lethal radiation. The K218 appears to be what astronomers call a well-behaved red dwarf with minimal flare activity that allows its planets to maintain stable atmospheres and potentially support life. The stable energy output of K218 creates conditions that are remarkably similar to Earth's, despite the star being much smaller and cooler than our Sun. Goldilocks zone. The planet K218b orbits much closer to its star than Earth orbits the Sun, completing one orbit in just 33 days. But because the star is cooler, this close orbit places the planet in the perfect position to receive almost exactly the same amount of energy per square meter as Earth receives from our Sun. This cosmic coincidence means that K218b exists in what astronomers call the Goldilocks zone, not too hot, not too cold, but just right for liquid water to exist on the surface. But unlike Earth, which will eventually be destroyed when our Sun expands into a red giant, K218b could remain in this perfect zone for trillions of years, providing an almost unlimited timescale for life to evolve and develop. Tidal locking. The gravitational relationship between K218b and its star has also created tidal locking, where one side of the planet always faces the star, while the other remains in perpetual darkness. This might seem like a disadvantage, but the planet's thick atmosphere redistributes heat so efficiently that both sides maintain comfortable temperatures. The result is a world with a permanent day side and permanent night side, each offering different environments for life to explore and exploit. K218 represents more than just a star. It's a promise of cosmic stability that could nurture life beyond our wildest dreams. The 120 light-year journey. The distance to K218b is both impossibly vast and tantalizingly close. 120 light-years means that the light we're seeing from this world left its surface when Teddy Roosevelt was President of the United States. It's a distance so enormous that our fastest spacecraft would take over 2 million years to reach it. Yet it's practically next door in cosmic terms. To put this distance in perspective, imagine shrinking the entire Milky Way galaxy to the size of North America. Earth would be smaller than a grain of sand, and K218b would be another grain of sand about the width of a small town away. In a galaxy containing over 100 billion stars, K218b is close enough that we can study its atmosphere in detail, analyze its chemical composition, and detect the signatures of life itself. The light that carries information about K218b's atmosphere has traveled through the vacuum of space for 120 years, crossing vast emptiness between stars while carrying the molecular fingerprints of an alien world. When that light finally reaches the mirrors of the James Webb Space Telescope, it's so faint that Webb must collect photons for hours just to detect the presence of a single molecule in the planet's atmosphere. A cosmic time machine. But distance works in our favor as well as against us. The 120 light-year journey acts like a cosmic time machine, allowing us to observe K218b as it existed over a century ago. The dimethyl sulfide signatures we're detecting were produced by living organisms when Earth was just beginning to industrialize. We're literally seeing the breath of alien life from the past. The implications of detecting life at this distance are staggering. If we can identify biosignatures on K218b from 120 light-years away, it means the biological activity on that world must be enormous. The organisms producing dimethyl sulfide aren't just surviving, they're thriving on a planetary scale, creating atmospheric signatures so strong they can be detected across interstellar space. The local galaxy. This distance also makes K218 be a perfect target for future observations. While it's too far away for any conceivable human mission, it's close enough that we can study it in extraordinary detail with increasingly powerful telescopes. The upcoming extremely large telescope, with a mirror over 100 ft across, will be able to analyze K218b's atmosphere with unprecedented precision, potentially detecting dozens of different biosignatures. The 120 light-year distance places K218b within what astronomers call the local neighborhood of stars. This region contains several thousand star systems, many of which likely harbor planets. If life exists on K218b, it suggests that our local galactic neighborhood might be teeming with living worlds, each developing their own unique biospheres and evolutionary paths. Perhaps most remarkably, the distance to K218b means that if there's intelligent life on that world, they could be detecting signs of life on Earth right now. The radio signals we've been broadcasting into space for the past century are just reaching their neighborhood, potentially announcing our presence to any civilization advanced enough to detect them. We're not just discovering life on a distant world, we're potentially making first contact across the vast darkness between stars. Impossible, the solution came from an unexpected source, studying our own sun. For decades, astronomers have used devices called coronagraphs to block out the sun's blinding light and observe its corona, the faint outer atmosphere that's normally invisible against the star's brilliant surface. Webb's engineers adapted this technology for exoplanet detection, creating what might be the most sophisticated light-blocking system ever devised. The coronagraph. Webb's coronagraph works like a carefully engineered eclipse. A series of precisely shaped masks and mirrors block the star's light while allowing the much fainter light from orbiting planets to pass through. But this isn't just a simple disk blocking the star. It's a complex system of multiple masks, each designed to eliminate specific types of light contamination. The tolerances are so precise that a misalignment of just a few billionths of a meter would ruin the entire observation. The coronagraph's performance is measured in something called contrast ratio, how much fainter the planet is compared to its star. For K218b, this ratio is approximately 10 billion to 1. To put this in perspective, imagine trying to spot a single candle burning next to the brightest stadium lights during a night game, while looking through a telescope from the opposite side of the country. The coronagraph makes this impossible task routine. Speckles and algorithms. But blocking the star's light is only half the battle. Once the starlight is removed, astronomers must deal with what they call speckles, tiny imperfections in the telescope's optics that create false signals mimicking planets. Advanced computer algorithms analyze these speckles in real time, using artificial intelligence to distinguish between genuine planetary signals and optical artifacts. The processing power required is staggering, equivalent to analyzing millions of photographs simultaneously to find one specific face in a crowd. The coronagraph's success depends on Webb's unprecedented stability. The telescope must maintain its position in space with an accuracy of milliarcseconds, equivalent to holding a laser pointer steady enough to hit a dime on the moon. Any vibration, any drift, any slight movement would blur the delicate observations and make planet detection impossible. Wavefront correction. Perhaps most remarkably, the coronagraph doesn't just block light. It actively shapes it using a technique called wavefront correction. The system constantly adjusts the incoming light to create the perfect conditions for planet detection. It's like having a cosmic lens that can bend and focus light in ways that reveal hidden worlds orbiting distant stars. The coronagraph technology that revealed K218b represents just the beginning of a revolution in exoplanet detection. Future telescopes will use even more advanced coronagraphs capable of detecting Earth-sized planets around sun-like stars, potentially revealing dozens of worlds where life might exist. But the coronagraph's greatest achievement isn't just technological, it's philosophical. By allowing us to see worlds that were previously invisible, it has opened a window into the cosmic neighborhood we never knew existed. Planetary habitability. When astronomers first calculated the mass of K218b, they discovered something that challenged everything they thought they knew about planetary habitability. The planet weighs in at 8.6 times the mass of Earth, making it roughly similar to Saturn in terms of total mass. Yet, unlike Saturn, which is a gas giant with no solid surface, K218b appears to be a water world with conditions that could support life more effectively than Earth itself. The relationship between planetary mass and habitability is complex and counterintuitive. On Earth, we're used to thinking of our planet's size as perfect for life, large enough to hold onto an atmosphere, small enough to maintain comfortable surface gravity. But K218b proves that bigger can actually be better when it comes to supporting life over cosmic time scales. Gravity and atmosphere. The planet's massive size creates surface gravity nearly 3 times stronger than Earth's. While this might seem like a disadvantage, the intense gravity serves crucial functions that actually enhance habitability. The strong gravitational field holds onto the planet's atmosphere with an iron grip, preventing it from bleeding away into space, like Mars lost its atmosphere billions of years ago. Even the most violent stellar flares from the host star cannot strip away K218b's thick atmospheric envelope. This gravitational advantage extends to the planet's ability to retain water. On Earth, we lose water to space through a process called atmospheric escape, where water vapor in the upper atmosphere is broken apart by solar radiation, allowing hydrogen to drift away forever. K2-18b's powerful gravity prevents this loss, creating a world where water can accumulate over billions of years rather than gradually disappearing. Super Earth. The planet's mass also affects its internal structure in ways that benefit life. The intense pressure at K2-18b's core likely prevents the formation of the kind of solid iron core that Earth possesses. Instead, the planet may have a water ice core surrounded by layers of liquid water hundreds of miles deep. This creates a planetary ocean that dwarfs all of Earth's oceans combined, providing an enormous environment for life to develop and diversify. Perhaps most importantly, K2-18b's mass places it in a sweet spot that astronomers call the super-Earth category. These worlds are large enough to maintain thick atmospheres and deep oceans, but not so large that they become gas giants like Jupiter or Saturn. The boundary between rocky super-Earths and gaseous mini-Neptunes appears to be crucial for habitability, and K2-18b sits precisely in this optimal range. The planet's mass also influences its thermal evolution. Larger planets retain heat longer, potentially maintaining warm conditions for trillions of years, while Earth's interior is slowly cooling and will eventually become geologically dead. K2-18b's massive size means it could remain geologically active for periods longer than the current age of the universe. This long-term geological activity could drive the carbon cycle and atmospheric chemistry that maintain stable conditions for life. The discovery of K2-18b revolutionizes our understanding of planetary habitability. We're no longer looking for Earth's twin. We're looking for Earth's bigger, more stable, longer-lived cousin. In a universe where super-Earths are more common than Earth-sized planets, the galaxy might be filled with worlds where life has advantages we never imagined possible. Debris disks. Sometimes the most important discoveries come from what's not there rather than what is. The James Webb Space Telescope's discovery of another potentially habitable world designated this world around the star called CE Antil came not from detecting the planet directly, but from spotting a suspicious gap in the debris disk surrounding the young star. This gap, like a cosmic fingerprint, revealed the presence of a hidden world shaping the structure of an entire stellar system. Debris disks are the leftover construction material from planetary formation, composed of dust, ice, and rocky fragments that orbit young stars in vast rings. These disks are like cosmic construction sites where planets are still forming, gathering material from the surrounding debris to grow larger and more massive. But when a planet forms within a debris disk, it acts like a cosmic vacuum cleaner, sweeping up material in its orbital path and creating a clear gap in the disk. The CE Antil discovery. The debris disk around CE Antil is particularly spectacular when viewed from Earth because we see it face-on rather than edge-on. This gives astronomers a bird's-eye view of the disk structure, revealing details that would be invisible in edge-on systems. The disk is divided into 3 distinct rings, each separated by gaps that suggest the presence of planets shepherding the material into organized patterns. When Webb turned its infrared eyes towards CE Antillae, it spotted something extraordinary in one of these gaps, a faint infrared source that could only be explained by the presence of a previously unknown planet. The object now called this world has a mass similar to Saturn, but orbits in the gap between the first and second debris rings, exactly where computer simulations predicted a planet should exist based on the disk's structure. The discovery represents a new way of finding planets. Instead of waiting for worlds to pass in front of their stars or detecting their gravitational effects, astronomers can now identify planets by the gaps they create in debris disks. This technique, called direct imaging, allows scientists to study planets that might never transit their stars from Earth's perspective, vastly expanding the number of worlds we can discover and analyze. A young world. But the debris disk around CE Antil revealed more than just the presence of a planet. The structure of the disk suggests that this world is actively shaping its environment, clearing out material in its orbital path while simultaneously shepherding debris into the organized ring structure. This planet isn't just passively orbiting its star, it's actively sculpting the architecture of its entire stellar system. The temperature of this world, measured at approximately 120 degrees F, places it in the potentially habitable zone, where liquid water could exist on its surface. The planet's position within the debris disk also suggests it's young, possibly still in the process of gathering material and growing larger. We might be witnessing a world in the early stages of its formation, before it has had time to develop the complex atmospheric chemistry that characterizes mature planets. The debris disk discovery demonstrates that planetary formation is an ongoing process throughout the galaxy. Young stars are constantly creating new worlds, and Webb's ability to peer through cosmic dust allows us to watch this process in real time. We're not just discovering planets, we're witnessing the birth of new worlds. New worlds. The discovery of life on K218b was just the beginning. As the James Webb Space Telescope continued its survey of nearby star systems, a pattern began to emerge that would revolutionize our understanding of life in the universe. The galaxy isn't just home to a few scattered habitable worlds. It's teeming with planets that could support life, each offering unique conditions and possibilities for biological development. Within a sphere of just 200 light-years around Earth, astronomers have now identified over 50 planets that show signs of habitability. These worlds range from super-Earths like K218b to smaller rocky planets orbiting in the habitable zones of red dwarf stars. Each represents a different experiment in planetary evolution, a unique set of conditions that could give rise to life unlike anything on Earth. The diversity of worlds. The diversity of these potentially habitable worlds is staggering. Some orbit close to their stars with thick atmospheres that create runaway greenhouse effects, maintaining liquid water at temperatures that would boil away Earth's oceans. Others exist in the outer reaches of their stellar systems, kept warm by internal heat sources and thick atmospheric blankets. A few show signs of global ice coverage with subsurface oceans that could harbor entire ecosystems hidden beneath frozen surfaces. But it's not just the number of habitable worlds that's remarkable, it's their variety. Different types of stars create different types of habitable zones, each favoring different kinds of life. Red dwarf stars, which make up 3/4 of all stars in the galaxy, create habitable zones that last for trillions of years, giving life essentially unlimited time to evolve complexity. More massive stars burn brighter and faster, creating habitable zones that might favor rapid evolution and adaptation. Billions of possibilities. The statistical analysis of these discoveries is breathtaking. If the local neighborhood around Earth contains 50 potentially habitable worlds within 200 light-years, then the entire galaxy might contain billions of planets where life could exist. The Milky Way, with its 400 billion stars, could be. Implications. Home to more living worlds than there are people on Earth. Each of these worlds represents a different solution to the challenge of supporting life. Some might have evolved oxygen-rich atmospheres like Earth, supporting complex multicellular organisms that breathe and photosynthesize. Others might have developed hydrogen-based biochemistry, creating ecosystems that would seem utterly alien to Earth. A few might have taken evolutionary paths that we haven't even imagined yet. The implications for the search for extraterrestrial intelligence are profound. If life is common throughout the galaxy, then intelligent life might be equally widespread. The radio telescopes scanning the skies for signals from alien civilizations might not have to search for long. In a galaxy teeming with living worlds, the question isn't whether intelligent life exists elsewhere. It's how many civilizations are out there trying to contact us. But perhaps most remarkably, the discovery of multiple habitable worlds suggests that life itself might be a fundamental feature of the universe. Just as stars form when gas clouds collapse under gravity, life might emerge naturally wherever conditions allow. We're not alone in the universe. We're part of a cosmic community of living worlds that spans the entire galaxy. The universe is more alive than we ever dared to imagine. The water universe. Water is the universal solvent, the medium in which life as we know it can exist. But the water on K218b isn't just any water. It's water that exists in quantities and conditions that dwarf anything found on Earth. The planet's vast oceans, potentially hundreds of miles deep, represent the largest known reservoir of liquid water in the universe outside our solar system. The presence of water vapor in K218b's atmosphere was one of the first clues that this world might be habitable. When the James Webb Space Telescope analyzed the planet's atmospheric composition, it found clear signatures of H2O molecules absorbing specific wavelengths of infrared light. But the amount of water vapor detected suggests something extraordinary. the planet's atmosphere is saturated with moisture, indicating vast oceans. On Earth, our oceans contain about 350 million cubic miles of water, covering 70% of the planet's surface to an average depth of just over 2 miles. But K2-18b's oceans could contain 1,000 times more water, creating a planetary ocean that extends from pole to pole and reaches depths that would crush any Earth-based submarine. This isn't just a water world, it's a water universe where the liquid environment provides space for evolution on a scale impossible on Earth. Chemistry of the oceans. The chemistry of K2-18b's water is equally remarkable. Mixed with hydrogen from the planet's atmosphere, the water forms a solution that remains liquid across a much wider range of temperatures and pressures than pure water. This hydrogen-enriched water could support life forms that use hydrogen as an energy source, breathing the water itself while extracting energy from the dissolved gases. But the most important aspect of K2-18b's water might be its stability. On Earth, our oceans are gradually being lost to space as water vapor in the upper atmosphere is broken apart by solar radiation. Over billions of years, Earth will eventually become as dry as Mars. But K2-18b's powerful gravity and thick atmosphere prevent this water loss, creating oceans that could persist for trillions of years. The temperature of K2-18b's water, maintained at approximately 120 degrees F by the planet's atmospheric greenhouse effect, creates conditions that are not just habitable, but actively beneficial for life. This temperature accelerates chemical reactions and biological processes while remaining cool enough to prevent the breakdown of complex organic molecules. It's like having a planetary hot tub that's perfectly calibrated for life. Oceans as regulators. The water on K2-18b also plays a crucial role in the planet's carbon cycle. The vast oceans can absorb enormous amounts of carbon dioxide from the atmosphere, helping to regulate the planet's temperature and atmospheric chemistry. This creates a natural thermostat that keeps conditions stable over geological timescales, providing the long-term stability that complex life requires. Perhaps most remarkably, the water on K2-18b might be just the beginning. If super-Earths like this world are common throughout the galaxy, then the universe might be filled with water worlds where life has had billions of years to develop in oceanic environments far more extensive than anything on Earth. The discovery of K2-18b's vast oceans represents more than just finding water on another world. It's the discovery of a new category of planetary environment where life might thrive beyond our wildest dreams. Transmission spectra. Every molecule tells a story. When starlight passes through the atmosphere of K2-18b, it carries with it the chemical signatures of an alien world, creating what astronomers call a transmission spectrum, a cosmic fingerprint that reveals the planet's atmospheric composition with extraordinary precision. This fingerprint doesn't just tell us what gases surround the planet. It tells us whether life is actively changing the chemistry of an entire world. The process of reading atmospheric fingerprints is like cosmic archaeology. Each molecule in the planet's atmosphere absorbs specific wavelengths of light, creating dark lines in the spectrum that Webb can detect and analyze. Oxygen creates one pattern, water vapor another, methane a third. But when the James Webb Space Telescope analyzed K2-18b's spectrum, it found something unprecedented, a combination of molecules that could only be explained by active biological processes. Chemical disequilibrium. The atmospheric fingerprint of K2-18b reveals a world in chemical disequilibrium. In a lifeless atmosphere, chemical reactions would eventually reach equilibrium, creating a stable mixture of gases that doesn't. Chemical disequilibrium. Change over time, but K2-18b's atmosphere contains combinations of molecules that should react with each other and disappear. Yet, they persist in large quantities. This chemical imbalance is the signature of life actively pumping gases into the atmosphere. On Earth, our atmosphere is similarly out of equilibrium. We have both oxygen and methane in our atmosphere, gases that should react with each other and disappear. The only reason they persist is that living organisms are constantly producing both gases, maintaining the chemical imbalance that characterizes a living world. K2-18b shows the same type of chemical disequilibrium, suggesting that life there is actively shaping the planet's atmospheric chemistry. The detection of dimethyl sulfide in K218b's atmospheric fingerprint represents the strongest evidence yet for extraterrestrial life. This molecule is produced exclusively by living organisms and breaks down quickly in the atmosphere, so its presence indicates that something is actively producing it in vast quantities. The atmospheric fingerprint shows not just the presence of dimethyl sulfide, but also its distribution throughout the planet's atmosphere, suggesting that life on K218b is not confined to isolated pockets, but spans the entire world. Hints of alien biochemistry. But the atmospheric fingerprint reveals more than just the presence of life. It hints at the type of life that might exist on K218b. The high concentrations of hydrogen and methane suggest that the planet's organisms might use these gases as energy sources, breathing hydrogen and metabolizing methane in ways that would be impossible on Earth. The atmospheric chemistry points to a biosphere based on fundamentally different biochemical processes than anything in Earth's evolutionary history. Precision of Webb. The precision required to read these atmospheric fingerprints is staggering. Webb must measure the absorption of light at specific wavelengths to an accuracy of 1 part per million, detecting molecular signatures so faint that they represent just a tiny fraction of the total light from the star. It's like identifying a single person's voice in a crowd of millions, but the voice is carrying information about life on another world. The atmospheric fingerprint of K218b will go down in history as the first chemical signature of extraterrestrial life. It's proof that life doesn't just exist elsewhere in the universe. It's actively transforming entire worlds, creating atmospheric signatures that can be detected across the vast distances between stars. CE Antle, a cosmic nursery. The star system around CE Antle is a cosmic nursery where worlds are still being born. At just 6.4 million years old, this red dwarf star is barely out of its stellar infancy, still surrounded by the disk of debris from which planets continue to form. But this youth comes with a price. The violent processes of stellar and planetary formation create conditions that would seem hostile to life, yet might actually be essential for creating the complex chemistry that life requires. Young stars like CE Antle are notoriously unstable, prone to massive flares that can increase their energy output by thousands of times for hours or days. These stellar tantrums bombard nearby planets with radiation intense enough to strip away atmospheres and sterilize surfaces. Yet the planet discovered in this system, with its surface temperature of 120 degrees F, appears to have not only survived these violent outbursts but potentially benefited from them. The debris disk. The debris disk surrounding CE Antle shows ongoing planetary formation. The disk is divided into 3 distinct rings, each containing different types of material at different stages of assembly. Innermost ring right arrow fine dust and rocky fragments clumping into planetesimals. Middle ring where the new planet orbits, containing larger chunks of rock and ice swept up by the planet's gravity. Outer ring right arrow pristine material, untouched by planetary formation. This ongoing accretion process means the planet is still growing, gathering material from the surrounding debris disk and potentially increasing its mass over time. The violent collisions between the planet and debris create conditions of extreme heat and pressure that could drive the complex chemistry necessary for life. Each impact brings new materials and energy to the planet's surface, creating a dynamic environment where chemical evolution can proceed rapidly. Stellar chemistry factory. The young star's high energy output also drives atmospheric chemistry in ways that might be crucial for life. Intense ultraviolet radiation breaks apart simple molecules in the planet's atmosphere, creating reactive fragments that can combine into more complex compounds. This stellar chemistry factory might be producing the organic molecules that serve as the building blocks for life, seeding the planet with the raw materials for biological evolution. Sculpting the disk. But perhaps most remarkably, the planet appears to be gravitationally sculpting the debris disk, creating the gaps in structure that allowed astronomers to discover it. The planet's gravity shepherds material in the disk, clearing out its orbital path while simultaneously gathering material to fuel its continued growth. This dynamic interaction between planet and disk creates a feedback loop that could accelerate both planetary formation and the development of complex atmospheric chemistry. Life in a chaotic system. The discovery of a potentially habitable world in such a young system challenges our assumptions about when life can emerge. If life can develop in the chaotic environment of a forming planetary system, then the universe might be filled with worlds where biology and geology evolve together, creating conditions for life that are far more robust and adaptable than anything we see on Earth. The violence of stellar birth might not be an obstacle to life. It might be the crucible in which life learns to thrive in the most extreme conditions the universe can create. The mysterious gap. In the debris disk surrounding CE Antillae, there's a gap that defies explanation by conventional physics. The empty space between the first and second rings of debris should be filled with dust and rocky fragments, yet it's almost completely clear of. The mysterious gap. Material, this gap stretching across millions of miles of space, can only be explained by the presence of a hidden world that has swept up all the material in its orbital path. The gap represents a cosmic mystery that took years to solve. When astronomers first observed the CE Antillae system with ground-based telescopes, they could see the overall structure of the debris disk, but couldn't determine what was creating the empty spaces. The gaps were too large to be explained by magnetic fields or pressure waves, and too clean to be the result of random collisions. Something massive had to be clearing out the material, but that something was invisible to conventional telescopes. The James Webb Space Telescope's infrared vision finally revealed the answer. Hidden in the gap was a faint infrared source, glowing with the heat of a young planet that had swept up all the debris in its orbital zone. The planet, now designated this world, has a mass similar to Saturn, but orbits much closer to its star, creating gravitational forces strong enough to clear out a gap millions of miles wide. Precision of the gap. The precision of this gap is what makes it so remarkable. Planetary formation theory predicts that growing planets should create gaps in debris disks, but the gap around this world is almost perfectly clean, suggesting that the planet has been in its current orbit for a significant period of time. This challenges our understanding of how quickly planets can form and begin affecting their environment. But the gap tells a deeper story about planetary formation. The clean edges of the gap suggest that the planet's gravity is not just clearing out material, but actively organizing it. The debris that would normally orbit chaotically is being shepherded into the ring structures that frame the gap, creating a complex gravitational dance that shapes the architecture of the entire system. Gravitational architecture. Computer simulations of the CE Antillae system reveal that the planet's gravity creates resonant zones where debris can accumulate safely without being swept up by the planet. These zones correspond exactly to the locations of the observed rings, confirming that the planet is actively sculpting the structure of the debris disk. The planet isn't just orbiting passively, it's acting as a cosmic architect, designing the layout of its stellar system. The gap also provides clues about the planet's composition and history. The material that has been swept up by the planet includes water-rich comets and asteroids, suggesting that the world has acquired the volatile compounds necessary for developing atmospheres and potentially supporting life. The planet's current temperature of 120 degrees F indicates that it has retained enough of this material to maintain a substantial atmosphere. 120 degrees F, the cosmic sweet spot. Perhaps most remarkably, the gap suggests that planetary formation is a more orderly process than previously thought. Instead of random collisions and chaotic accumulation, planets appear to create organized structures that persist for millions of years. The gap around this world represents not just an empty space, but a footprint of gravitational architecture that reveals how worlds shape their cosmic neighborhoods. 120 degrees F, this temperature appears again and again in the most promising discoveries of potentially habitable worlds, as if the universe has found the perfect setting for life to flourish. It's warm enough to drive rapid chemical reactions and maintain liquid water, yet cool enough to prevent the breakdown of complex organic molecules. On multiple worlds discovered by the James Webb Space Telescope, this temperature represents the sweet spot where life can not only survive but thrive. Why 120 degrees F matters. The significance of this temperature extends far beyond simple habitability. At 120 degrees, water exhibits properties that are ideal for supporting life. The liquid is warm enough to dissolve a wide range of chemical compounds, creating solutions that can transport nutrients and waste products efficiently. The temperature accelerates biochemical reactions, allowing metabolic processes to proceed at rates that support active life while remaining slow enough to maintain stable molecular structures. But 120 degrees F also represents something more profound, the temperature at which Earth's most extreme life forms thrive. Lessons from Earth. In deep-sea hydrothermal vents, where temperatures reach similar levels, life has evolved some of its most remarkable adaptations. These environments host organisms that use chemical energy instead of sunlight, creating ecosystems that are completely independent of surface conditions. The discovery of worlds with similar temperatures suggests that such chemosynthetic life might be common throughout the universe. The temperature also creates ideal conditions for the formation of complex organic molecules. Laboratory experiments have shown that temperatures around 120 degrees F are optimal for the synthesis of amino acids, the building blocks of proteins. This temperature range allows for the chemical reactions that create life's essential molecules, while preventing the thermal breakdown that would destroy them at higher temperatures. Different paths to 120 degrees F. On multiple worlds, this temperature is maintained by different mechanisms, each revealing a different pathway to habitability. Some planets achieve this temperature through atmospheric greenhouse effects, where thick atmospheres of hydrogen or carbon dioxide trap heat from their stars. Others maintain 120 degrees through internal heat sources, where radioactive decay or gravitational compression provides the energy to warm the surface. A few worlds use a combination of both, creating remarkably stable temperature conditions. The consistency of this temperature across different planetary systems suggests that it might represent a fundamental optimum for life. Just as stars have preferred masses and sizes that allow them to burn stably for billions of years, planets might have preferred temperatures that allow life to develop complexity and diversity. The evolutionary advantage. The temperature of 120 degrees might be the cosmic setting where biology works best. Perhaps most remarkably, this temperature creates conditions that are not just habitable, but actively beneficial for life. The warmth accelerates evolution by increasing mutation rates and metabolic activity, while the stability prevents the temperature extremes that could drive species to extinction. Life on these worlds might evolve faster and more diversely than life on Earth, creating biospheres of unprecedented complexity. The perfect temperature. The perfect temperature suggests that the universe might be fine-tuned for life in ways we're only beginning to understand. The temperature sweet spot isn't just a coincidence. It might be the signature of a universe where life is not just possible, but inevitable. The methane mystery on K2-18b. Methane should not exist in the atmosphere of K2-18b. This simple molecule, composed of one carbon atom surrounded by 4 hydrogen atoms, is highly reactive and breaks down quickly when exposed to ultraviolet radiation. Yet, the James Webb Space Telescope has detected substantial amounts of methane in the planet's atmosphere, creating a mystery that can only be solved by the presence of life actively producing this gas on a planetary scale. On Earth, methane is produced by a variety of biological processes. Bacteria in swamps and wetlands produce methane as they decompose organic matter in oxygen-free environments. Microorganisms in the digestive systems of animals create methane as they break down food. Even some plants produce methane as part of their metabolic processes, but all of these sources share one common characteristic: they're biological. No known geological process on Earth produces significant amounts of methane. Methane on K2-18b tells a story of active biological processes that might be even more prolific than those on Earth. The concentrations detected by Webb are orders of magnitude higher than what would be expected from geological sources, suggesting that the planet's biosphere is producing methane at rates that dwarf anything seen on Earth. This isn't just life surviving on an alien world. It's life thriving and reshaping atmospheric chemistry on a global scale. Biochemistry beyond Earth. But the methane mystery goes deeper than just production. The molecule's presence in K2-18b's hydrogen-rich atmosphere creates possibilities for biochemistry that don't exist on Earth. Methane can serve as both a carbon source and an energy source for organisms, potentially supporting ecosystems that breathe methane and metabolize it for energy. In the planet's unique atmospheric chemistry, methane might be as important to life as oxygen is to Earth-based organisms. The interaction between methane and hydrogen in K2-18b's atmosphere could create complex organic molecules that serve as the building blocks for life. Laboratory experiments have shown that methane and hydrogen can combine under the right conditions to form amino acids, the components of proteins. The planet's atmospheric chemistry might be acting as a giant biochemical factory, producing the organic compounds that life needs to develop complexity. A stable biosphere. The methane also provides clues about the planet's evolutionary history. The molecule's presence suggests that K218b has maintained active biological processes for extended periods, possibly millions or billions of years. This indicates that the planet's climate and atmospheric chemistry have been stable enough to support life over geological timescales, creating conditions where evolution can proceed toward increasing complexity. Perhaps most remarkably, the methane on K218b might be just one component of a much larger atmospheric ecosystem. The planet's atmosphere contains a complex mixture of gases that interact with each other in ways that could support multiple types of metabolism. Different organisms might use different atmospheric components as energy sources, creating a layered ecosystem that spans the entire atmosphere from surface to space. The methane mystery represents more than just a chemical puzzle. It's evidence of a living world where biology and atmospheric chemistry have co-evolved to create conditions that support life on a scale beyond anything in Earth's history. The planet's atmosphere isn't just a mixture of gases. It's a living system that breathes with the rhythm of an entire biosphere. A new era of discovery. The discoveries made by the James Webb Space Telescope on K218b and other potentially habitable worlds represent just the beginning of a revolutionary observation campaign that will reshape our understanding of life in the universe. Armed with the knowledge that biosignatures can be detected across interstellar distances, astronomers are preparing an unprecedented survey of nearby star systems that could reveal dozens of living worlds within the next decade. The next phase of observations will focus on what astronomers call the Biosignature Survey, a systematic search for the chemical signatures of life in the atmospheres of planets orbiting nearby stars. This campaign will target over 200 star systems within 100 light-years of Earth, analyzing the atmospheric composition of every potentially habitable world that can be observed. The goal is nothing less than creating the first comprehensive catalog of life in our cosmic neighborhood. The Biosignature Survey. Webb's upcoming observations will use increasingly sophisticated techniques to detect fainter biosignatures in smaller planets. New observing modes will allow the telescope to study planets that don't transit their stars from Earth's perspective, vastly expanding the number of worlds that can be analyzed. Advanced computer algorithms will search for complex combinations of molecules that could indicate not just life, but different types of life based on alternative biochemistry. The observation campaign will also focus on time series analysis, studying how atmospheric compositions change over months and years. On Earth, our atmosphere shows seasonal variations as life responds to changing conditions. Similar variations on exoplanets could reveal not just the presence of life, but active biological cycles that respond to planetary seasons, stellar activity, or other environmental changes. Technosignatures, signs of intelligence. One of the most exciting aspects of the next observation campaign is the search for what astronomers call technosignatures, the chemical evidence of technological civilization. Industrial processes produce distinctive atmospheric pollutants that could be detected across interstellar distances. The observation of artificial gases in an exoplanet's atmosphere would provide the first direct evidence of technological intelligence elsewhere in the universe. The campaign will also coordinate with other observatories around the world and in space. Radio telescopes will search for artificial signals from star systems where Webb detects biosignatures. Optical telescopes will look for signs of artificial lighting on the night sides of potentially inhabited worlds. This multi-wavelength approach will provide the most comprehensive search for life and intelligence ever attempted. The future of observations. Future observations will benefit from technological advances that are already in development. Improved coronagraphs will allow Webb to study smaller, more Earth-like planets. New spectrographs will provide higher resolution analysis of atmospheric. Advanced imaging and life detection. Advanced image processing techniques will extract more information from the same observations, potentially revealing biosignatures that are currently below the detection threshold. The observation campaign represents more than just a scientific program. It's humanity's first systematic attempt to map the distribution of life in the galaxy. Within the next decade, we may have identified hundreds of living worlds, each with its own unique biosignature and evolutionary history. The universe may reveal itself to be not just habitable, but abundantly alive. The next observation campaign will answer the greatest question in science. Are we alone? The answer appears to be a resounding no, and we're about to discover just how much company we have in the cosmos. The three-ring circus of C. Antle. The debris disk surrounding C. Antle resembles a cosmic three-ring circus, with each ring containing different types of material at different stages of planetary formation. This organized structure reveals that planetary formation is not a chaotic process, but follows predictable patterns that create order from cosmic chaos. The three rings around C. Antle represent different chapters in the story of how worlds are born. The innermost ring, closest to the star, contains the finest dust and smallest rocky fragments. This material is heated by the star's energy to temperatures that would melt lead, yet it maintains a stable orbit in a narrow band just a few million miles from the stellar surface. The particles constantly collide and stick together, gradually building larger aggregates that will eventually become the cores of rocky planets. The middle ring, where the newly discovered planet orbits, contains a mixture of rock and ice that tells the story of a world in the process of formation. Conditions here allow both rocky and icy materials to exist, creating the complex chemistry that could lead to habitable worlds. The planet discovered in this ring has cleared out most of the original material, but the remaining debris shows evidence of ongoing accretion and growth. The outer ring, composed largely of water, ice, and organic compounds that have remained frozen since the star's formation. This ring serves as a reservoir of volatile materials that could be delivered to inner planets by gravitational perturbations or collisions. It represents the deep freeze of planetary formation, where the building blocks of life remain preserved in cosmic cold storage. Patterns of planetary formation. The spacing between the rings is not random, but follows mathematical relationships that reveal the gravitational architecture of the system. Each ring occupies a zone where orbital mechanics create stable conditions for material accumulation. The gaps between rings represent areas where gravitational resonances disrupt orbits, preventing material from accumulating and creating the clean boundaries that separate the rings. The three-ring structure also reveals the timeline of planetary formation. The innermost ring shows the earliest stages, where dust grains are just beginning to stick together. The middle ring represents the intermediate stage, where planet-sized objects are clearing out their orbital zones. The outer ring shows the preservation of original material, waiting for the right conditions to begin its own journey toward planetary formation. Computer simulations of the C. Antle system reveal that the three-ring structure is not static, but evolving over time. Material slowly spirals inward from the outer rings, feeding the growth of planets in the inner system. The newly discovered planet acts as a gravitational barrier, preventing material from the outer rings from reaching the inner ring too quickly. This creates a controlled feeding process that allows planets to grow steadily over millions of years. A window into planetary birth. The three-ring circus around C. Antle represents more than just a cosmic structure. It's a window into the universal process of planetary formation. Similar ring structures have been observed around other young stars, suggesting that the organized chaos of planetary birth follows similar patterns throughout the galaxy. We're not just observing one stellar system, we're watching the universe manufacture new worlds. A record-breaking discovery. The planet discovered by the James Webb Space Telescope in the C. Antle system has broken a fundamental record in exoplanet science. With a mass just one-third that of Jupiter, this world is the lightest planet ever directly imaged around another star. This achievement is more than just a technological milestone. It demonstrates that Webb can detect and analyze worlds remarkably similar to planets in our own solar system. Previous direct imaging of exoplanets was limited to massive worlds, typically several times Jupiter's mass. These superjupiters were easier to detect because their large size and high temperatures made them bright enough to be seen despite the glare of their host stars. But the newly discovered world around C. Antle is 10 times less massive than any previously imaged planet, pushing the boundaries of what's possible with current technology. Challenges of detection. The planet's low mass creates unique challenges. Less massive planets are cooler and dimmer, making them much harder to distinguish from the bright background of their parent star. The light from this world is nearly 10 billion times fainter than the light from C. Antle, requiring Webb to operate at the absolute limits of its sensitivity. The fact that the telescope can detect such a faint object is a triumph of engineering and data analysis. But the planet's low mass also makes it scientifically fascinating. Objects with masses similar to Jupiter represent a boundary in planetary formation between gas giants and smaller rocky worlds. This planet sits right at that boundary, providing crucial insights into how planetary systems transition from massive gas giants to smaller terrestrial worlds. Understanding this transition is key to predicting where habitable planets might form. Toward Earth-like worlds. The planet's mass also affects its potential for habitability. While Jupiter-mass planets are typically gas giants with no solid surface, this lighter world might have a solid core, surrounded by a relatively thin atmosphere. The surface temperature of approximately 120 degrees F suggests it retains enough atmospheric mass to maintain a greenhouse effect, but not so much that it becomes a runaway gas giant. Detecting this low-mass world required innovative observational techniques. Webb's infrared instruments had to distinguish between the planet's faint thermal emission and the brighter, scattered light from dust in the debris disk. Advanced image processing algorithms removed the contaminating light, revealing the planet's faint infrared glow. The entire process was like extracting a whisper from a thunderstorm. The planet's thinner atmosphere makes it an ideal target for future atmospheric studies. More massive planets have thick atmospheres that hide deeper layers from observation, but this world's atmosphere allows Webb to probe more directly into its composition. A golden age of discovery. The detection of this low-mass world proves that Webb can find and study planets genuinely similar to those in our solar system. This opens the possibility of discovering and analyzing truly Earth-like worlds, bringing us closer to finding planets that might not just be habitable, but actually inhabited. The lightest world ever imaged has opened a new chapter in the search for life beyond Earth. The discoveries made by the James Webb Space Telescope are just the beginning of a golden age in the search for extraterrestrial life. The rising confidence. The statistical confidence will rise from 99.7% to 99.99%, then to certainty beyond any reasonable doubt. When that moment arrives, the implications will ripple through every aspect of human civilization. Science will be revolutionized as we grapple with the reality that biology is not unique to Earth, but a fundamental feature of the universe. Philosophy and religion will be transformed as we reconsider humanity's place in a cosmos that contains other forms of life. Technology will advance rapidly as we develop new methods to study and potentially communicate with life on distant worlds. The psychological impact on humanity will be profound. The knowledge that we are not alone will end the cosmic loneliness that has haunted our species since we first looked up at the stars and wondered if anyone was looking back. We will become members of a galactic community of living worlds, each following its own evolutionary path, but sharing the fundamental experience of life in the universe. A new responsibility. But the moment will also bring new responsibilities. As we identify more living worlds, we will face ethical questions about our obligations to protect and preserve life throughout the galaxy. The discovery of extraterrestrial life will force us to develop new frameworks for understanding our relationship with the cosmos and our responsibilities as a spacefaring species. The moment we're no longer alone will mark the beginning of a new chapter in human history. We will transition from a species that wonders about life elsewhere to a civilization that knows life exists throughout the galaxy. The transformation of the universe. The universe will be transformed from a vast empty space into a cosmic ecosystem, teeming with biological activity and evolutionary experimentation. Looking back from that moment, we will recognize that the James Webb Space Telescope's discovery of biosignatures on K2-18b was the first step in humanity's journey from cosmic isolation to galactic citizenship. The chemical signatures detected in the atmosphere of a world 120 light-years away will be remembered as the evidence that ended our loneliness and began our understanding of our place in a living universe. The moment we're no longer alone is almost here, and everything is about to change. The evidence of life. We stand at the threshold of the greatest discovery in human history. The James Webb Space Telescope has peered across 120 light-years of space and found something that will change everything we thought we knew about our place in the universe. In the atmosphere of K2-18b, wrapped in hydrogen clouds and warmed to exactly 120 degrees F, life is breathing. The evidence is overwhelming. Dimethyl sulfide, a molecule produced only by living organisms, exists in concentrations detectable across interstellar space. The statistical confidence is 99.7%, as certain as any fact in science. The atmospheric chemistry tells a story of biological processes operating on a planetary scale, transforming the air of an entire world through the collective breath of countless organisms. A galaxy alive. But K2-18b is not alone. Webb has revealed a universe where potentially habitable worlds exist in abundance, each offering unique conditions for life to emerge and thrive. From the debris disks around young stars where planets are still forming, to the ancient red dwarfs that will burn for trillions of years, the galaxy appears to be filled with environments where life can not only survive but flourish. The implications extend far beyond astronomy. We are witnessing the end of humanity's cosmic loneliness and the beginning of our recognition as citizens of a galactic community. The universe is not empty space punctuated by rare pockets of life. It is a vast ecosystem where biological processes operate on scales that dwarf anything in Earth's history. The next era. The technologies that made these discoveries possible represent just the beginning. Future observatories will reveal the atmospheric signatures of hundreds of living worlds, each with its own unique biochemistry and evolutionary history. We may discover forms of life based on completely different chemistry than what we see on Earth, expanding our understanding of what life can be and how it can emerge. The moment we definitively confirm that we are not alone will mark a turning point in human civilization. Every child born after that moment will grow up knowing that life exists throughout the galaxy, that we are part of a cosmic community that spans the stars. The philosophical and spiritual implications will reverberate through every aspect of human culture. But perhaps most importantly, these discoveries remind us that life is not just possible in the universe, it appears to be inevitable. Wherever conditions allow, life emerges and transforms worlds. The living universe. The chemical signatures detected by Webb are not just evidence of life on distant planets. They are proof that the universe itself is fundamentally alive. The James Webb Space Telescope has given us the first glimpse of our true cosmic neighborhood, revealing that we live in a galaxy where life is not the exception but the rule. We are no longer alone, and we never were. The universe has been waiting for us to develop the technology to see what was always there, a cosmos teeming with life, breathing with the rhythm of countless biospheres, alive with possibilities we are only beginning to imagine. The universe is alive, and we are part of its story.